let's get into this last session of all this. So let's now start to look at this as a useful method, a useful framework to do Bayesian inference. And as I said, next week you're going to hear an awful lot more about Bayesian inference and Bayesian non-parametrics and Bayesian modelling and so forth. And in large part, you will have to think about sampling and so forth. And you will have to think about it seriously, because some of these models will be highly structured, pretty complex, and will therefore induce quite a complex space from which you have to sample from. So these ideas are going to be really important. So now what I'm going to do is just talk about a whole load of applications, and as I said, look at strengths and weaknesses, and discuss some open issues. Okay, mixture models. There was a time when you could pretty much publish any paper on mixture models of some description with the EM algorithm, and it seems to be going the way of the Swiss roll data set. But they still are very important models where you have some probability distribution over observables, and it's described by a mixture of some other probability distributions. So Neil very briefly alluded to the probabilistic PCA. Because you now have PCA in terms of a probabilistic model, and therefore it induces a distribution over observations conditioned on the structure of the model, which in this case is the PCA model, you can then look at things like mixtures of probabilistic PCAs and so forth. So I'm just going to focus on a really simple mixture model, very classical one, which is just a mixture of Gaussians. Now, the Fissure Information metric tensor for the mixture of Gaussians turns out to be non-analytic. Well, that's a great start, right? The very first application, and we can't get an analytic expression for the metric tensor of the model. But what we can do is we can employ the empirical Fissure information. So in other words, an empirical estimate of the expectation under the sampling distribution of the covariance of the score. And it turns out to be fairly straightforward. I know that Neil loves his matrix notations, so we can write the metric tensor for our mixture model based on the empirical Fissure information as just this inner product of these matrices and these vectors. And these matrices just are composed of the score of the overall log likelihood of the model, and that's pretty much it. And then the derivatives of the metric tensor for the connection, of course, are, well, just follow via standard differentiation. So we have all the geometric components that we need for our model. We can then just plug these into our manifold metropolis adjusted Langevin method. We can just plug it into our Hamiltonian scheme and define the geodesics on the space defined by this empirical Fissure information, and off we go. So here's a very simple example. It's a Gaussian mixture which comprises two components, and we know the mixture weights, which we normally wouldn't, and the parameters are such that the mean of the first component is known, the mean of the second component is a random variable, and the variance of both components is shared. Now, the reason that I have done this is to ensure that this is an identifiable model, and we don't have this rotation or this label switching problem to contend with, which is another complication when we deal with mixture models we're doing inference over mixture models in a Bayesian setting, right? But it's a sufficiently rich representation to really illustrate the ideas. And so this is the posterior distribution over mu and log sigma for this mixture model. And what I've shown here are the gradients, and the sort of ellipses represent the region of influence, if you will, of the inverse of the metric tensor. So one of the things that you can see is that in this part of the space you've got these very, very large gradients, and then in this part of the space here you've got these very small gradients. You've got this big plateau. So for those of you who are familiar with optimization or so forth, what you would see is that you'd be able to move very quickly in these regions here, and in many ways you could move far too quickly because the gradient might actually get you to overshoot into sort of uninteresting regions. But when you get into this sort of region here, then the gradients are going to be very small and you're going to make reasonably slow progress. And so what we see, if I take the standard Mala method, this is the metropolis adjusted Langevin algorithm, where I'm not taking into account the geometry of the model, what we see is exactly that. We see that initially we can make these large steps in the Markov chain, again because of the large gradients. And then of course once we get onto this plateau, you can see that the movement is extremely slow. Once we converge, you can see here that the autocorrelation is dreadful, right? So in the non-stationary phase of the chain, you can see that convergence is going to be very slow, and then once we've converged, sampling is going to be very inefficient. Of course, that's the reason why we designed it like this, so that we could show this sort of phenomenon. But it's a very common phenomenon, especially in an awful lot of natural systems, as well you would have seen if I had about 20 hours to give lectures. On the other hand, had I now employed the manifold on which this mixture, the geometry of the manifold on which this mixture representation resides, now we can see that the gradient structure is such that it doesn't cause the Markov chain to make enormous jumps, right? But we have this, how can I put it, this kind of normalization of the steps in the chain, and so we have a kind of more, okay, we're moving slightly slower here, but we're doing it in a more sort of considered way. But then once we reach the plateau, we're making these nice large moves. More importantly, once we actually converge, you can see that the autocorrelation is, I mean, it's almost independent sampling. If we discount the connection, so if we just assume that the curvature is constant, then we don't really tend to lose very much in the overall chain. Okay, so that looks nice. But if I then go to the Hamiltonian scheme, where I'm now using these geodesics, what do we have? Well, here's the standard Hamiltonian Monte Carlo. Now, it does an awful lot better than the metropolis adjusted Langevin, but remember that we're not taking into account the metric structure, and therefore we get these, you know, large responses to extreme gradients, and then, you know, things start to slow down, but not as drastically, because, you know, of the multiple steps that are being used in the Hamiltonian scheme. And then again, once we actually do converge, then the performance is really pretty impressive. But when we employ the geodesics, then we see something like this, and I think this is really nice because you can see again as soon as we reach the plateau, you know, it's almost taking one proposal to actually converge. And again, we've almost got independent sampling. Now, if we use the actual Gibbs sampler itself, this is what the Gibbs sampler gives us, which isn't bad. And the performance is actually, you know, as good as the Hamiltonian Monte Carlo method. Now, we did a whole series of experiments on various distributions and various applications with this, and certainly with the set of distributions that we looked at, the effective sample size, right, that was generated from the Markov chains was consistently improved when we employed the manifold style methods. And there's a chapter in a book on mixture models by Mengerson and Christian Robert, where one of my colleagues, one of my postdocs, actually developed all of this for univariate mixtures, multivariate mixtures, and various other types of mixtures. So this was quite nice. But now I want to go on to some really challenging problems. So here's a model that's used and is very important in financial modeling, stochastic volatility model. So we want to model the volatility of various trades and so forth. And the model is described as follows. The actual observed volatilities at a time t are distributed in this form here. Right, so we have this exponential of this x of t, and this x of t is the latent volatility. So this is the underlying volatility of the process, right, that's driving these trades. And the underlying process is an autoregressive process of order 1. Okay, so it's a Markov process of order 1. And the two parameters here, epsilon t, is just a standardized Gaussian. And the parameter beta, well, we'll put a prior on that just shortly. The autoregressive process, again, is going to have a parameter phi, which we'll put a prior on. And then the innovation is, again, just a Gaussian with mean of 0, and it has a variance structure, sigma squared, which again we'll put a prior on. And the latent volatility at time step 1, this just pops out from the distributions for the AR1 process. So what we observe are the volatilities. What we're interested in are the parameters phi, sigma, and beta. So 3 parameters, so it's hardly a high-dimensional problem. What we don't observe, on the other hand, are the latent volatilities. And we have one latent volatility for each observed volatility. And typically, we would observe a time series of about 2,000–3,000. So we're going to have a latent space of dimensionality 2,000–3,000. And because we don't observe this, we're going to have to do inference on this in some way. So we're going to have to get a posterior distribution over these and then try and marginalize over them. And none of this is analytic, incidentally. So what was looking like a potentially easy problem, just 3 parameters, turns out to be 3 parameters of interest plus another couple of thousand latent variables which we need to characterize a posterior over as well. So this turns out to be not a straightforward problem. It also turns out to be not straightforward because computing the likelihood is highly challenging as well. So we're going to be Bayesian And again, I'm sure you're going to be fully card-carrying Bayesians by the end of next week. So I'm just buttering you up at the moment. But if we write out the joint distribution of our observed volatilities, the latent volatilities, which you don't know anything about, apart from the fact that they follow an AR1 process, and the three parameters of the model, well, we just take this product form, right? So we have the probability of our observations given our latent variables and the parameters. The distribution of the latent variables follows this AR1 process, and this is characterized by these two parameters. One is the scaling, and one is the variance of the innovation. Beta here is the multiplicative factor that appears in the likelihood. And then we've defined three priors, and we've just made them three independent priors. And I'm not going into the details of what these are. You'll find them, a lot of details about them in the paper that I'm going to refer to at the end of the talk. But suffice to say, there are constraints. So for example, to ensure that the AR1 process is stable and so forth, then phi has to lie within a particular range, and therefore we need to have certain transformations to ensure that phi lies within the stable range and so forth. So that there's an awful lot of complexity in this model right at the very start in terms of doing inference. Now what we're interested in is the posterior of the parameters conditioned on our observed data y. X, the latent volatilities, are just a nuisance. So one thing that we would like to do is we'd like to say, well, can we marginalize X analytically? And you see lots of clever papers and NIPS where they manage to find a nice, elegant marginalization and so forth. But the reality is that in most difficult applications, you typically don't have that, that analytic convenience. So one way that we can obtain samples of our parameters given our data is we can split up the sampling scheme. We can use a product kernel. Remember the product kernel from the first lecture? And we know that devising a product kernel, we can break up the sample, we can break up the parameters into convenient blocks. And we still know that, you know, sampling from the conditional distributions of each of those blocks still gives us the overall target distribution. So what we could do is we could say, well, we could devise a sampler for the parameters conditioned on the data and some values of the latent volatilities that we'll obtain somehow or other. And so that's just going to be equal to this here. And then, given the parameter values, we could then sample the latent volatilities via this here. So this defines a product kernel, and we will definitely be able to sample from P of beta, phi, sigma, x conditioned on y. And if you remember from the product kernel, if we're sampling from that joint distribution, then the betas, the phis, and the sigmas will be marginally distributed according to the posterior of interest probability of beta, phi, sigma conditioned on y. Well, let's now have a look at how we're going to devise this sampling scheme. We're going to use the manifold methods because this is a very difficult problem. So if we just take this first distribution here, then if we look at what the metric tensor is for this, it turns out that after some tedious algebra, the metric tensor looks something like this here. Okay, so this is the metric tensor for this conditional distribution. So we can devise some manifold sampling scheme for this conditional distribution. That's great. Now what about sampling from this 3,000 dimensional distribution? Well, it turns out that the metric tensor for the latent volatilities looks something like this. Now what is this? Well, it's half times an identity plus the inverse of this matrix C, this 2,000 dimensional, 2,000 by 2,000 dimensional matrix. But it turns out that C, because this is an AR1 process, actually has a very simple structure. It turns out, so you can see that the metric tensor here is a function of the parameter values, or two of them anyway. Here, on the other hand, the metric tensor is constant. So it defines a flat manifold in the latent volatility space. So we can now use these to define RMHMC or manifold Mala sampling schemes for both of these, and we can truck on. So you saw this the other day there, where I showed you the random walk for this stochastic volatility model for two of the parameters. And here is the Riemann manifold Hamiltonian method. Now, do you remember with the Hamiltonian Monte Carlo, we made this enormous jump, and then we kind of fiddled about here for a while, and then we converged quite quickly. Well, here there's no fiddling about, and there's no fiddling about because there's no mismatch between the metric that's being used to make proposals of the Markov chain and the metric that's defining the actual model manifold. So very, very rapid convergence and very, very efficient sampling. So what we've done is just to get a ground truth, we've taken a number of, we've taken some parameter values, right, which we've set, and we've then simulated 2,000 observed volatilities, and we've then run this sampling scheme. So we've got high dimension, and we've got very strong nonlinear interactions, and we've also got a high degree of non-analytic representation. So the effective sample size, so out of the 20,000 posterior samples that we simulated from once the Markov chain eventually converged, what we see is that if we just use the standard Langevin proposal, so not taking the geometric structure into account, out of 20,000 posterior samples, then only 19 for the beta parameter were effectively independent. Only 11 for sigma, only 30 for phi. Right? And the amount of time, the number of wall clock seconds that it took to obtain an effective sample, an independent sample, was about just under 4 seconds. HMC, on the other hand, the effective sample size, well, it grows by, well, an order of magnitude at best. The amount of time it took was much longer. So if we normalise by the amount of time taken, it actually does a poorer job than the Langevin scheme. I guess if I cut to the chase, if I use the geodesics as defined by the manifold itself, so this RMHMC, so we've now got about 2 orders of magnitude improvement in the effective sample size, and the relative speed, right, of producing independent samples has improved somewhat as well. But what you see here is that the efficiency, right, we need to generate 20,000 posterior samples to get, roughly 300 independent samples. So this is not good. And this is not good because this is a hard problem. A very hard inference problem. If we look at the sampling of the latent volatilities, then the story is pretty similar. 20,000 posterior samples of these 2,000 latent volatilities. And with the manifold schemes, again, it's doing okay. It's about the same as HMC in this case. And that would make sense, because the manifold is flat. So you're not going to lose as much by just assuming a Euclidean metric, right? And that's clear to see here. But still, because of the improved statistical efficiency, the amount of time taken to generate independent samples is still improved. So this is good. And this is one of the things you should look at when you read papers and they say we used Hamiltonian Monte Carlo on this very exotic Bayesian model and this is what we got. You should ask yourself the question, one, did the sampler really converge? Are these samples, these posterior samples, going to be any use in terms of actually doing any proper Bayesian inference? And how much time did it actually take to generate these? Right? If you're going to be Bayesian, you might as well do it properly. So what this suggests is that this stochastic volatility model is within a class of problems that is hard. It's really hard. So let me move on to another model. This should please Neil, because it's a log Gaussian Cox point process on a latent field. And if I interpret that in machine learning language, it's a Gaussian process with a likelihood which is Poisson. So I'm observing counts. So what we're modeling is a field, two-dimensional field, and at random points on that field there are measurements and they are integers. And this is a very important type of model for epidemiology, for ecology. In fact, one of the big applications of, and for other things where there's a spatial element, in neuroimaging, so we're working with neuroscientists and actual clinicians who are using functional magnetic resonance imaging to try and characterize certain regions of the brain that are affected by certain diseases and so forth. And so one of the types of models that are used is something like this here. In ecology, I have colleagues who go to Greenland every summer and throw cameras down into the water and take photographs of the biodiversity at various regions under the sea, to understand and characterize the effect of intensive fishing. And so on it goes. In epidemiology, I'm sure Neil is familiar with this, we would be able to characterize the number of events of the incidence of particular types of disease, again in various geographical locations. And we want to be able to have a probabilistic model to understand certain interactions between location, geography, and certain covariates or features that are available. So this is a very important class of probabilistic model, and one which is very much deserving of a Bayesian treatment. So here we have a latent field, X. So what we're saying is that there's some continuous process which we don't observe that gives rise to the discrete observations, the discrete counts that we actually are able to measure. So X turns out to, the components of the Gaussian process are just simply the locations in the spatial field. X, as I said, is going to be the value of this continuous process within the field. And that's something we don't observe. And then there are a set of parameters associated with the covariance structure, covariance function, or the kernel, if you will, which drives this process. And then conditional on this latent process, we have a Poisson process which, whose mean is defined by the value of the latent field. So what we now have is a very similar situation to the stochastic volatility model. We have observations which are now discrete counts, right, at the number of trees or the number of black frogs or whatever at each of these individual locations. So these are our observations. The latent variable is the value of the underlying field, which we can't observe. And then we have a series of parameters, mainly associated with the Gaussian process. So we need to do inference on this. And similar to the previous model, we're going to have to use a product kernel. We're going to have to split up the sampling by sampling the latent field conditional on the data and the current value of the parameters. And then we're going to have to sample the parameters given the current sampled values of the latent field and the data. Now in this example here, the latent field is of order 4,000. So this is high dimensional. The number of parameters, again, is only 3. So it should be fairly straightforward. Well, in actual fact, it's not fairly straightforward. This is one of the big challenges for Gaussian processes. So I think a lot of work has been focused on Gaussian processes on being able to either sample or approximate various moments of the posterior distribution for the latent functions, the latent fields. And we've pretty much got a good handle on that. But the really important area now to investigate is how do we actually do posterior inference over the parameters which drive the covariance function. And that turns out to be a much harder, a much more challenging proposition, which I'm going to talk about just shortly. When am I meant to finish? 5 minutes ago? Yeah. Do you want me to continue for another 10 minutes? Or are you done? Continue. God bless you. So if again, cutting a long story short, and you can read the details, the technical details in the paper, but if I define the metric tensors for the latent field, again it turns out that for a Gaussian process, the metric tensor for the latent field, for the latent functions, happens to be constant. Right? So the manifold has constant curvature, it's flat. And the metric tensor for the parameters of the Gaussian process takes on this analytic form here, which looks pretty horrendous because you've got these inverses and then these derivatives of the metric tensor, or in this, so I beg your pardon, derivatives of the covariance function and so forth. So you can see we're now starting to crank up the computational complexity. So the latent field, the metric tensor, it defines a flat manifold which is about 4,000 by 4,000 dimensional, and of course this is going to scale at worst as order n cubed because this metric tensor is not going to have any nice structure similar to the AR1 process. This is going to be fairly dense unless we do something clever in terms of the choice of covariance function. Now, if we use something like the Langevin scheme or hybrid Monte Carlo without employing the metric structure or without using some sort of explicit transformation of the latent field, and without tuning the sampling scheme both in the transient phase and in the stationary phase of the Markov chain, the thing will not converge, it will just fall flat. And I was really grateful to Neil when he spent quite a bit of time describing the intuitions about what happens to a Gaussian when you move from 1 dimension to 2 dimensions to 3 dimensions, and the mass starts to concentrate in this kind of annulus. Do you remember? So things are kind of strange. And because of that, it means that when you're trying to sample in that space, then things are going to be very difficult. And because we're in essence sampling in a 4,000 dimensional Gaussian space, right? You know, we've got this very thin annulus that we can only move in. And so if we don't take into account that structure which emerges from the metric, then we're going to be in a hiding to nothing, and that's exactly what happens. Whereas if we use the manifold methods and we employ the natural geometry, all of that concentration in this thin annular shell doesn't pose a problem, because that geometry has been taken explicitly into account in the sampling scheme. And here is some data. And here are the posterior means, right, that we obtain when we actually sample the latent field. And we do a pretty good job. And, okay, that looks like a nice picture. But here's some of the problems. So if we use RMHMC, then this is the value of the posterior. So you can see that we pretty much converge. So if we start at the mode and we start sampling, then we've got beautiful mixing. If we use the manifold Mala method, again starting at the mode, we get almost good mixing, pretty good mixing. On the other hand, if we use the Langevin scheme and we don't use the intrinsic geometric structure, we start at the mode, then because of this concentration of the mass, then strange things happen. So although we've started at the mode, it actually jumps away from the mode, and then it takes a fair bit of time to get back to it. And the key thing here is that if we actually tune the Langevin scheme for the stationary distribution, then it never moves at all. And we don't have that problem when the intrinsic geometry is taken into account. Now look at this. So the Mala scheme tuned in the transient phase, well, look at this for the effective sample size. This is not good. Whereas for the Riemannian approach, this is for 5,000 posterior samples, we're almost getting independent sampling, and we're getting about 3 orders of magnitude of speed up. Now this is just on the latent space. So that's the good news. On the latent space, on the latent function space, if we take the geometry into account, we can almost obtain independent samples, despite how large the dimensionality is. Now what if we actually look at the parameters? Well, the sampling for the parameters turns out to be much more problematic, and the effective sample size, despite the use of the geometric structure in this Gibbs style sampling, or this product style sampling scheme, does not help us in any way. Now this is a serious problem. So I don't want to keep you any longer, but there's some very interesting work that was done for logistic regression with Gaussian process priors by Ian Murray and Ryan Adams. And what they showed was that if they used a whitening transformation, then they could improve the sampling. Well, of course, the whitening transformation is nothing more than transforming the random variables using the metric tensor. So in many ways, they found a specific instance of this more general sampling scheme, employing the metric structure. But the problem, again, as I say, is still the sampling of the parameters of the covariance function. And this is still a very much an open question. And one of my postdocs at the moment is working on a scheme for employing the underlying geometry of a Bayesian hierarchical model, such as the Gaussian process style model that we've seen from Neil, and I'm sure you'll see plenty more hierarchical models next week. I'm clearly not going to have any time to talk about this, but this is really fascinating because there's another geometric structure in Riemannian manifolds which are called foliations. And these are these are submanifolds of the overall manifold structure. You want me just to stand still and get that photograph? I moved too much, I know. And they can be devised in such a way that the foliations define a submanifold which enforces a statistical orthogonality between the latent function values and the parameter values, and it breaks the correlation structure which destroys the efficiency of all of these sampling schemes. And so we've got great hopes for that, and we'll see what happens in the future. So these are the foliations. Very beautiful example, but I'm not going to get time to talk about that, I'm afraid. So let me conclude and then throw some ideas to you if you're hungry for ideas for PhDs or so forth. So what I've tried to convince you is that the geometry, the underlying geometry of statistical models, of probabilistic models, can be harnessed in a very useful way in Monte Carlo methods. Now, I spoke about diffusions with respect to structure and the curvature of the space, this manifold mala. I showed you how we could exploit the geodesic flows on the model manifold by employing this Riemannian manifold Hamiltonian Monte Carlo scheme, which is a generalization of the HMC, and it fixes an awful lot of the shortcomings of HMC. And we assessed it on quite a number of very challenging problems. As I said, there are another two sets of slides where I look at problems in biomedical science, where we are dealing with well, some very complex statistical models, very complex probabilistic models, and you can look at some of the results. So if you go to my group's website, you'll be able to look at some of the papers that have appeared in journals such as Science and so forth, where we employ this sort of this scheme. Well, we've assessed it and correlated in high-dimensional latent variable models, which is sort of the standard fare for machine learning, and the capability of the methodology is very promising. Now, what about ideas for investigation? Well, there's a lot of computer scientists here, and a lot of machine learning people are very fixated on computational aspects, as they should be. And so, of course, one of the big potential computational bottlenecks is going to be the computation of the metric tensor and the various components of the connection. Especially as you go to high dimensions, you've got to invert these matrices, or you've got to certainly solve the systems associated with those matrices. And this is something that needs to be addressed. And someone asked the question, could you use something like the BFGS style schemes? And it's possible that you can, although with BFGS you break the Markov property unless you do something clever, which no one hasn't come up with just yet. I mentioned the theoretical analysis of the convergence, and some work has already started on that by some applied probabilists looking at the Langevin style schemes, and the theoretical analysis suggests very strong results for these geometric methods. And of course, one of the big open questions is, well, what are the rates of convergence? What are the optimal step sizes, asymptotic optimal step sizes for the Riemannian manifold Hamiltonian schemes and so forth? Now, furthermore, we have automatically gone for the Fissure information, the expected Fissure information, as the natural metric structure. But there's absolutely no reason why, well, there's a very good reason actually why we should use it. But there's no reason why you should be constrained to that. You may want to look at other metric structures based on different types of norm or different types of divergence. And there is a lot of work that needs to be done on characterizing these divergences and characterizing the geometries, and what are the aspects of the geometry that are really suited for devising an MCMC method that converges quickly and samples efficiently. So the design and the effect of the choice of the metric tensor. Actually characterizing formally the optimality of Hamiltonian flows as local geodesics, and then looking at alternative transition kernels based on different connections and so forth. But let me just say that this is not the cure-all. Right? Inference over Bayesian models of Bayesian probabilistic models is challenging, right? And there is no one cure-all. And I'm not for 1 minute saying that this is a silver bullet, but it's a very powerful methodology for the Monte Carlo toolkit. Now, there was a paper published not that long ago, and it's already gathering an awful lot of citations, much to my relief, called Riemann Manifold, Langevin and Hamiltonian Monte Carlo Methods. This is Riemann, this is a manifold, this is Langevin, this is Hamilton, and this is the casino in Monte Carlo. And this was a paper that has now been published in the Journal of the Royal Statistical Society, Series B. If you go to the journal website, you can download it free. So you could download it now, and you can download the paper. And the paper is published along with discussion. And so people like C.R. Rao contributed to the discussion, David Cox, a number of machine learning people, Carlo Rasmussen, who else? Dan Roy, various others. Anyway, it turns out that the paper is just over, or just under 100 pages long. But the discussion is really worth reading. It's full of great ideas by some really clever people, both from the statistics community and the machine learning community. And as I said, you should have a look at it. And there's code available to allow you to replicate all of the results that are in the paper, and the code's actually commented as well. And this is the paper here. So I guess that's me. I've taken far too long, but I'm leaving today, and I wanted to get to this, this part. Thanks very much for being so patient. I know this has been very difficult stuff, but I hope you would agree that it's very exciting. It's challenging, but it's really exciting. And I think after next week, once you have heard the talks by Zubin and the hardcore Bayesians, you'll see that there really is a place for this sort of methodology. So thanks for being very patient with me. I've kept you far too long, but I'm going to leave today, so I won't have to bear any complaints from you. So thanks very much. I guess the only question is what's happened to our 30-minute break, so I'll leave you.
Let's start at 20 past, okay? And you have cold coffee where you know.
Yeah, cold coffee.